teşekkür ederim. Well, I'm going to talk in English, just to speed things up a little bit. Learning the impossible. Okay, there you go. So, and let's see if I can get this to work. Yes, that's me. So I'm not going to waste a lot of time talking about myself, but there's one thing that I want to mention. I'm not an AI expert. I'm an end user. So I want to be very frank about that. I want to give you a perspective of a roboticist using AI. And I have a lot of questions. I'm going to give you my presentation, present you some results. Of course, this work, I did it with my students. Most of the work, most of the credit goes to them. But I have some questions. Maybe some of you can give me some insights about those questions. I want to give you an end user perspective. So we're just using artificial intelligence, machine learning actually, to try to solve some real life problems that we face in robotics. So yes, well, that's me. Let me skip this. But one thing that is important here is that I'm a roboticist and I love marine environment. I want to spend all my time underwater or above water, so most of my projects are directed towards that. And one of the projects was related to underwater robotics. So some time ago, we realized that there's a lot of robots. There was a fleet of about 2,000 robots when we first started to talk about this underwater robots. And mainly these robots only fit into these two categories. So there was ROVs that do something underwater, that are used to do something underwater, but they're very clumsy, very manual, very little automation on them. And then there was AUVs, autonomous vehicles, that just explore the environment, but they have no capability of interacting. So we wanted to come up with a system. We thought that there was something missing there, a capable robot, an autonomous robot that can also do dexterous manipulation underwater. And the reason for this is, whether you like it or not, we as humans are depleting our resources here above, on Earth, above water, on land, and the world is just not enough for us. So we've started to focus to the underwater and marine environment. And of course, now we're a little bit more clever about this. We want to do this in a sustainable way. And there's a huge, vast area, square meters on Earth, that we don't actually exploit. Now, sustainable exploitation of underwater resources, marine resources, is one problem or one solution that people are proposing for a remedy for the approaching resource crisis. Energy resources, food resources, calorie resources, minerals, valuable metals, etc. So, and there's a lot of other applications, military search and rescue. The more we use the marine environment, the more we need to interact with it, the more we will be present there, and we need to have capable systems to be able to do this. So that was the whole motivation of this project. And well, we wanted to look at nature. What are the most capable swimmers? What are the most capable manipulators, creatures that can actually interact with the environment? How do they do this? Octopuses, squids, cuttlefish, these are animals that are very, very dexterous. They have a lot of dexterous capabilities. They're experts. Maybe you've seen, I don't have it here, but you might have seen the octopus opening up a jar back in 2014, 10 years ago, and so on and so forth. So we envisioned a squid, a robotic squid with some autonomous capabilities as well as some dexterous manipulation capabilities. And the key here was there was a lot of different technologies, maybe 10 technologies that we wanted to test, and these are all new. Maybe they have been implemented in the terrestrial domain, above land, they have been implemented on land, they have been implemented, but they were never tried underwater, so we said, let's go ahead and test this. Now, of course, the main issue here, the main selling point of this project is to have dexterous, capable arms, these are the applications. So that was the key point there, and of course, we went to nature, as I said, and octopuses and cuttlefish and squids, they are probably the most capable creatures that you can find on underwater for manipulation. So I have a few videos here. I'm not sure if they play, but they're really cool videos of how octopus can reach out, grab something, grasp it, and bring it back in. So, you know, we actually studied all these, and we said, let's build an arm, a robotic arm, a limb that is kind of similar. So it should be soft, and it should take different forms. We should be able to do a lot of so-called motion primitives, you know, reach out, grasp something, bring it in, and so on and so forth. So we sat with that objective of, you know, designing this soft arm. Of course, this is a, you know, this is a huge divergence from your typical manipulator that you see in a factory environment, rigid links, joints, etc. And there's a wealth of theory on this, on how you can control it, how you can model it, how you can analyze it, how you can build it. So we know everything, but when you go on and talk about, you know, soft materials, squishy materials, none of that theory works. So you need to start from scratch. We started to work on this back in 2015, and nowadays there's a greater body of knowledge about this, but back then it was just empty. People were just starting to work on this. So we tried to model it. You know, tendons, the real animal has the whole body, the whole arm is a muscle. That's really, really difficult, a huge challenge. So we said, let's do something simpler. We have tendons to actuate it. We pull on these tendons. We have hyperelastic, very squishy material. And we tried to model this. We came up with a few models. This is actually the whole actuation system that we designed. So there's a lot of stuff that goes into it. And I mean, people are doing this, but they tested in the laboratory environment. We had to design it so that we can deploy it in the field as well. So it should get out of the laboratory environment. It should be compact. It should be energy efficient, and so on and so forth. So anyway, we started to model this, and then based on the models, we started to do some lab tests. I'm really happy that the equations came out. I'm not going to explain the equations, but you see that they're really, these are the forward equations. So, you know, if I apply a force to my tendons, how does the shape change? It's governed by these equations, very nasty equations. And to solve these equations, they're not easy. It takes an iterative approach. There's a lot of backwards and forwards integration, differentiation, and so on and so forth. And this is the simple model. This is time independent. But, you know, everything's time dependent. So we had to also come up with a time dependent model, which kind of complicates everything. But you could write a code, a simple code, 200, 300 lines, maybe 400 lines, and even a simple tool like MATLAB will solve you these forward equations without any problem. The problem is, though, the forward equations are not useful. So what the forward equations does is you tell how much force you're applying to your tendons, cables, etc., and it gives you the shape. It gives you where what the arm is doing, basically. That's not what we want. What we want is to reverse this. I want to do something. I want to tell my model to do something, and I want to know what I should do in terms of my tendons, in terms of my actuators, to actually accomplish that motion, accomplish that task. Which means I need to inverse these equations. I need to reverse them. It turned out to be impossible. And nobody at the time has done this. I don't think anybody has done it now. There were people working on it, but we said this is an impossible problem to solve. If we can't solve this, we can't realize this robot. So what do? And like all users of machine learning and AI does, we looked into machine learning. And at that time, we had these transformer methods that were emerging, generative AI methods that were emerging. Really, there were some really good results on, you know, text generation and even, you know, image generation and so on. So as a matter of fact, this is an image that was generated quite some time ago. I don't know which software, but my student generated this. He just gave his research keywords and he got this picture, which was really cool, I think. So for the inverse models, we went into machine learning and we started to look into transformers, which was the hot topic. We started to work on this in 2018, 2019. Transformers were the hot topic, so we said, let's go ahead and jumpstart the research. Let's go ahead and look into this. We came up with two models. This is the first one we called Kinaformer. It's a static model. So you tell where you want to go to. You don't have any time constraints. You don't have anything. You have a simple model. And the model, the transformer model, actually gives you what kind of inputs you need to provide. So this was the first one. This was a relatively simple model. I'm not going to go into the details of this, but at the end, I do have references to my students' work, so maybe you can take a look at it, their theses and so on and so forth. So, and this is the structure of it, the architecture that we used for the static model. A lot of stuff, feed-forward layers, attention layers, self-attention layers, etc., that are quite useful in text generation. Again, they're really useful over here, but we also share the same problem. We know the method works. We can do different things to improve it. We kind of understand how we can improve it, but we don't actually know what it's looking for to solve this inverse model, because that would be something really valuable for us. Maybe that could help us go towards building an analytic model for the same inverse problem as well. That would be huge. But anyway, we got some fairly good results. We tested it in a simulation environment. We modeled our arm, which is the one that you see at the top left over there. And we also used a very well-known existing arm, which is the one that you see here at the bottom. They were modeled using different methods. One of them used the analytic model. The other one used something called a finite element model, which is a mechanical thing, so I'm not going to go into the details. The finite element models actually do really well in terms of inverse modeling as well, but the problem is we need to be able to deploy this, so it needs to run on an embedded system, which the finite element models can't do. And it also needs to run in real time or very close to real time. And that means we need to get we need to get results very fast. So that was the main shortcoming of the finite element model. In any case, we trained it. So I'm going to be skipping these training details. They're important, of course. It took some time for us to get there, but eventually, we got some results and they were really good. We benchmarked our method with the baseline feed-forward neural network at the time, and these results are errors in terms of centimeters. The top one, you see the estimation error in terms of the actual tensions that we need to have at the cables versus the estimated ones for a given target position. The top one is for our arm, the bottom one is for the academic standard or the golden standard arm that everybody's using. And the bottom boxes indicate the positioning error, which is probably more important. It's not really important if you actually estimate the forces very well. Eventually, if you do that, you should also get a very good result in terms of positioning your arm. But the bottom ones are important. It's the positioning error. And as you can see, with the transformer method, we were able to reduce the error by 100%, almost 100% with the static model. Now, and these are some, again, results that we got. Now, the static model is a static model. There's no time dependence on it. But we can run the static model sequentially, feeding it different points instead of trajectories. The left one, we just give it random points. You see our method's performance versus the feed-forward neural network's performance. And on the right, we have this pseudo-dynamic. We're giving it trajectory, but we're not giving it a time-dependent trajectory. We're giving it endpoints sequentially. So there's no time dependence over there. Again, our method performed a little bit better, especially compared to the FFN method, significantly better for following a trajectory without time dependence. Then we went, these are the simulations. Can we play them? Actually, it's just simulation results, videos. I don't know if I can play them. Let's see. I don't want to break something, but... Whoops. Okay, thank you. I'm not playing it, but somebody is. So the red dot is where we want to go to, and what you're seeing here is the solution that the inverse model is giving us. We think it's fairly well. We can maybe play the other one too. At the end of the day, you might be wondering, well, yes, your method performs better than the regular feed-forward method, but is it worth it? Well, that kind of a small improvement is also good for us because sometimes we need to work in very confined spaces, and the more accurate results we get, the better our method is. And okay, so yes. So moving on to the dynamic method. How am I doing on time? Okay. So the second method we call Dynaformer. Now, we did something slightly different here. We used reinforcement learning where the network actually learns what it's supposed to do. It learns the inverse model by trial and error. But that trial and error was a little bit problematic, and we got a little bit smarter when we started to do this. So we said, let's also formulate a model for the forward part as well. Yes, we have the analytic model. We can write a simple MATLAB code or C++ code, Python code, whatever, to actually do the forward analysis as well. But let's train a model for that too. And we started to train that model so that it would be better integrated to the inverse method, reinforcement learning method that we were developing. So this is the forward model. Again, transformers are used for it. I'm going to be skipping the details, but basically you have action values. Are you going to pull which cable by how much is the input that you have? P is the resultant tip position, which is the goal that you want to achieve, the thing that you want to learn, the outcome of the algorithm, and then you have some intermediate steps in between. The transformer architecture was used here, and then once we had the forward model, we started to train the reinforcement learning approach based on this forward model rather than the simulation environment. And we used a TD3 algorithm for learning the policy and so on and so forth. And again, we went ahead and tested this tested this method on the industry standard ARM that we had over here. We gave random inputs, and we looked at the algorithm actually gave random inputs to the tendons, and it looked at what result it got based on those random inputs, and it started to learn the inverse model. Okay, if I'm going to apply so much tension or so much displacement on this cable, it's going to move the arm in this direction, and so on and so forth. And if I want to go over here, I need to apply so much tension on the cables. And eventually, we again compared it with an LSTM because it's time dependent, it's sequential data now. It's a dynamic model. We compared it with an LSTM, very basic benchmark methods. And again, our method, the transformer, slightly outperformed the LSTM method, so we were kind of happy with those results. This was for the forward model, and then we went ahead and did some reinforcement learning on the inverse model. This is the block structure. So here you see at the bottom, you see the learn forward model, and then based on the forward model, we train the RL agent to learn the inverse model of the forward model. These are some validation and training data that we have based on the loss functions that we get. And this was the workspace that we work with. So, all these dimensions are, this is the spherical workspace of the arm that we worked in. And we decided to set a target position. So if we're within 10 millimeters, 1 centimeters of the goal, we say we're happy with our result. We've reached our target point. And with 150 episodes, we were always able to reach that. Reach that target point, and we achieved 100% accuracy over there. Again, we have a small video, very similar to what we have. I guess we can play it maybe, but it's going to be very similar. The only difference now is there's a reinforcement learning method that is running over here too, that has learned the inverse model. Now, coming towards the end, I guess I can move forward. Oops, yeah. So we have some conclusions. I guess the bottom line is we're outperforming conventional methods, so-called conventional methods with transformers. One thing that is important here is we can actually implement these methods on an embedded board, onboard the robot. And we're not yet achieving real-time performance, but we're very close to it. So in the underwater domain, everything moves very slow. There's a lot of inertia, a lot of friction, and you don't want to do things really fast. At least for us, especially if you're manipulating something, it's not like a factory environment. So for us, it was sufficient. We were satisfied with the performance. We could deploy it on board the robot using embedded hardware. No problems over there. Compared to traditional methods, yes, we have a little bit more training. We require a little bit more data. Our models are a little bit more bigger. But sometimes we get 100% improvement in terms of the positioning performance. Now, this was the stuff that we did, but we're not done yet. We're continuing to work on this, and we have some real important questions. For example, can we improve the real-time performance of this method? Generalization, this is really important. You change something on the robot, you don't want to retrain the data. It takes a lot of time. The way that we're handling this, for example, you change the material that you construct the robot with, or the temperature changes sometimes because it's squishy material, the behavior of the arm changes. So we're all inputting these. Normally the model is really small because it has only 4 inputs if you have 4 cables, 8 inputs if you have 8 cables. But we started adding these material properties, temperature, some very important design parameters. How many cables you have, where are these cables connected to? We're currently working on that. Now, another really interesting thing that I have is, and this is an open question, there's redundancy. These robotic arms are highly redundant, which means that if I want to go ahead and touch this point, even with my arm, there's multiple solutions. I can touch it like this, I can touch it like this, I can touch it like this. So we're learning something and it's working, but is the solution that we're getting the optimum solution? And how can we know if there's multiple solutions, and how can we choose among these solutions? Now, these are also open questions for conventional robotics, but people have been working on this since the 1980s, and there's a lot of accepted answers here. For soft robots, we don't have this. So we're actually working on that. Shape control is important, but we've also studied this, not the entire shape control, but selected points of the arm. We don't just want the tip to go somewhere, we want it to take a specific shape for grasping, for example. It looks like it's a little bit easier. Our first analysis on this seems like convergence and the models are a lot easier if you want to formulate the shape, which might be because of the previous item. There's only one solution for that shape. There's not multiple solutions. And then real-world applications, that's something that we're currently working on. We're working to deploy these arms on the robot. This is what we envisioned on the top left. And this is where we are at right now. The arms are not yet integrated to the robot. We're working on the arms in a laboratory setting. But we have tested, we have deployed the robot in a pool environment, and we're going to continue working on this with the arms included in the robot in the coming months, maybe years, I don't know. It's a very involved project. It takes a lot of time. There's some really interesting stuff here. Some of them are still not deployed on this robot, but okay. I said I would cut it short, but it took quite a lot of time. Sorry for that. It was a funded project by TÜBİTAK, so I need to acknowledge them. And the details of the algorithms, more detailed of the results, and why certain choices were made, you can find them. I'd like to thank Ahmet, my student who worked on developing the arms, modeling them, and building them, and Abdul Rahman, who actually was a PhD student who did all the machine learning stuff on generating these inverse models. So thank you for your attention.